Vectors in Rn. Vectors in R2 and vector operations. We'll begin by discussing what is a vector. So a vector is just a directed line segment. Often you'll hear it referred to as a line segment with both magnitude and direction. Again, direction is important. Magnitude is simply the length of the line. So the initial point, we always like to think of the initial point at the origin, and the terminal point lies at x1, x2, which is how we're actually going to describe the vector. So even though I could draw in the same vector starting at a different point, in this case at -1, 0, I would still think about shifting that over so that its initial point is at the origin, so that each of these vectors would be referred to as 2, 3. So that's how we talk about a vector, is in component form. We write the terminal point to represent the vector. When we're talking about vectors, the way that we're going to show that is going to be a lowercase, bold, non-italicized letter, and just a normal 2, 3. You might also see this in a column vector form, 2, 3. It means the exact same thing. You might also see X with the vector accent above it, or you might see 2, 3 with the sort of arrowed parentheses, which also means vector. So I just want to make sure that you're clear. All of those things mean the same thing. We're going to take a look now at some vector operations, and instead of showing you the math, because the math is super simple, the math here is component wise, which means x values go with x values, y values go with y values. So if I'm finding the sum of two vectors, I'm adding the x values, I'm adding the y values. You get the idea. I want to focus instead on what this looks like on your graph. So again, I'm dealing with vectors. I should have some arrows on there, but again, I haven't figured out how to do that in Desmos, so you'll have to use your imagination. Right now, I've got two vectors. The first is at 2, 3, and the second is at 3, -2. So that's vector u and vector v. Now, those are the two vectors that we're going to use so that you can understand how vector operations work. So we'll start with u plus v. And when we're adding two vectors together, essentially what I want you to visualize is that I'm going to u, and then from the end of u, I'm basically going to slide this green guy up here and go v from u. So that would give me this point right here. So this would be v again. And so my solution would be 5, 1. So this is often called the parallelogram rule because we can see that this would make a parallelogram. So I could either take v plus u or u plus v. Either way, I end up at 5, 1. And so my new vector is that vector 5, 1. So I could get rid of, not that line. I could get rid of this line. I could get rid of this line. This is my new vector, and this vector would be u plus v. So it doesn't matter how I get there, but I did want you to see that essentially you're going to get there either from u plus v or v plus u. And again, this is called the parallelogram rule because it's essentially giving you a parallelogram, and then it would be at the opposite end of the parallelogram. So that's vector addition. And again, mathematically, what we did is we took the x value for u, which was 2, plus the x value for v, which was 3, and added them together to get 5. And then the y value for u, which was 3, and the y value for v, which was -2, and add them together to get 1. So again, the math is pretty straightforward, but I did want you to visualize what that's going to look like. So let's get rid of all of that and take a look now at scalar multiplication. So for scalar multiplication, I'm going to take a look at u, and I'm just going to take u times 5. And if I take u times 5, that's going to give me the point 10, 15. Now, I do want to point out with scalar multiplication that my initial value of u is really part of that vector. So it's essentially u, and then I added u again, and added u again, and added u again, and added u again to get all the way out to 10, 15. Mathematically, I took 2 times 5 to get 10, and I took 3 times 5 to get 15. Either way, it got me out to 10, 15, which is my new vector, 5u. Again, I want to be very straightforward about the fact that u is a part of that original vector. It will make sense why I'm stressing that when we get to unit vectors in just a moment. So let's get rid of that vector and take a look at negating a vector. So I wanted to negate v simply because v already had a negative value. So v is at the point 3, -2. I'm going to negate 3 to get -3. I'm going to negate -2 to get +2. So my new value is going to be at -3, +2. So it's going to look, just like this, -3, +2. And that is the point -v. Lastly, I want to take a look at the difference of u and v. So this is u minus v. Again, mathematically, I'm just going to take the x values and subtract them. So this is 2 minus 3 would give me -1. For the y values, I have 3 minus -2, which would give me 5. So that's going to be right up here at the point -1, 5. Now, again, I want you to visualize what's happening. I can either think of this as u and then plus -v. Nope, hold on, wrong one. This guy. So this is u, and then I'm adding -v. So I'm taking this guy and just shifting him right up there, and that's going to get me there. Or I can think about -v plus u. And either way, I'm going to end up at that point, -1, 5. Again, parallelogram rule. And so this would be my new vector. So I can get rid of these other guys, and that would be my new vector, u minus v. Let's talk now about some properties of vector operations. We can see that 1 through 5 all have to do with addition. So u plus v is a vector in the plane. That means closure. Means if you take any 2 vectors in the plane and add them together, the result will also be in the plane. That one's going to be very important to us. Number 2, commutative property. We talked about this with the parallelogram rule. It doesn't matter the order in which you add vectors, you're going to end up at the same position. Same for 3. Associative property, we can group them differently and it's not going to change the outcome. For 4 is the additive identity property. And what I don't have here is that u plus the 0 vector is equal to u, but that means that the 0 vector is in the plane. Now I point that out because there's going to be 3 of these that are important to us, and one of them is closure under addition. One of them is that the 0 vector is contained in the plane, and we're going to skip over the additive inverse property, also important, u plus -u is equal to 0. But 6 is the other very important property that says cu is a vector in the plane, which is closure under scalar multiplication. Now, I point these out because these are the 3 that we're going to talk about in our next part of this video, which talks about vector spaces. Again, anything above that line is talking about addition, and anything below the line is talking about multiplication, scalar multiplication. Again, a scalar multiple, we know this, say 3 times the vector 1, 0. So 3 is a scalar because it's being multiplied by everything in the vector. So we've got distributive property, we've got the associative property with scalars, and we've got the multiplicative identity property. Vectors in Rn. Let's talk now about vectors in Rn. So we just talked a little bit, mostly about vectors in R2, but an ordered n tuple represents a vector in n space. So obviously this picture is in 2 space, but I could visualize a vector in 3 space, it gets much more difficult to visualize vectors after that point. So this is where things get a little bit more abstract. But essentially we're saying you're going to have ordered triple or an ordered quadruple or so forth, and all of those are going to be represented in Rn. So this picture would be R2, which would be 2-dimensional space. So just as in R2, each n-tuple can be viewed as a point in Rn with xi as its component. So the same way that we said 2, 3 would be 2 on the x1 axis and 3 on the x2 axis or y-axis, you could do the same for 3 space, 4 space, and so forth. If you're joining us from the last part of this video that talked about vector operations in R2, good news, those vector operations are the same. So if I'm finding the sum is just component-wise. If I'm finding the scalar multiple, I'm taking every element of that vector times the scalar multiple. If I'm finding the difference, again, it's component-wise. So what we're saying component-wise is if I'm taking u plus v, and now notice that these are written kind of as ordered triples, but if you would rather think of this as 3, 1, 2, plus v is 0, 1, negative 1. So these are the same thing. It's whatever makes the most sense to you. But if I'm adding, really I'm just adding the same position. So that would give me 3 plus 0 is 3. 1 plus 1 is 2. 2 plus negative 1 is 1. So when I say component-wise, that is what I'm referring to. I'm saying in the correct position. So 3 plus 0 is 0. 1 plus 1 is 2. 2 plus negative 1 is 1. So whichever way you think of it is fine. For B, notice we've thrown in some scalar multiple and a difference. So 2w would be taking w, everything in there times 2. So 2, negative 2, 2. And then we're subtracting 3. So I'm going to do what I always do, which is make it plus and take v times negative 3. So negative 3 times 0 is 0. Negative 3 times 1 is negative 3. And negative 3 times negative 1 is positive 3. And then I would add those together to get 2 plus 0, negative 2 plus negative 3, and 2 plus 3. So again, whether I write it as an ordered triple or as a column vector, really the results are the same. The same properties that we had for vector operations in R2 still hold for vector operations in Rn. Again, anything above this line deals with addition, and anything below the line with scalar multiplication. I'm not going to go over any of those in detail, except to point out again that we'll be focusing on 1, 6, and whether or not 0 is contained in the plane. Here are a couple of questions for you to try on your own. Now, this one does get a little bit trickier. The first one, we're solving for x and there's just one x. The second one, we're solving for x and there's 2 instances of x, which is going to make it a little bit more complicated. But I'd just like you to try your best. Try them both on your own. When you're ready, press play to see how you did. So for my first question, I have x by itself, and I'm going to take 2 times u. So 2 times u would be 6, 2, 4, 0. And I'm going to subtract, which means I like to turn that into plus and distribute the negative to make sure that I don't make any errors. So I'm going to add a negative v, so 0, positive 2, negative 1, positive 1, and negative 3w, so I'm going to take w times negative 3, and that's going to give me negative 3, 3, negative 3, 3. So my final solution is just to add component-wise, which is 6 plus 0 plus negative 3, 2 plus 2 plus 3, 4 plus -1 plus -3, and 0 plus 1 plus 3. 3704. Now for the second one, because I have more than one instance of x, I would do some algebra first. So instead of just starting to plug in u and v and w, I would solve this like a normal equation, trying to get x by itself. So this gives me 3x plus 3w by distributing that 3 is equal to 2u minus v plus x. Let's subtract 1x from each side. That gives me 2x plus 3w equals 2u minus v. Then I get 2x is equal to 2u minus v minus 3w. So x is 1/2 of 2u minus v minus 3w. Now here is where I would typically start plugging in values, but if you'll notice, I already found 2u minus v minus 3w. And so 2u minus v minus 3w, I already know is 3704. So my solution here is half of that. So 3/2, 7/2, 0, 2. Linear combinations of vectors. So a very important type of problem, and one that you'll see over and over again, not only in linear algebra, but especially in linear algebra, involves writing a vector as the sum of scalar multiples of other vectors. So in other words, I can take some vector x and write it as the sum of scalar multiples of v1, v2, and so on. We call that a linear combination of the vectors. So let's take a look at an example. We have x is -1, -2, -2, and then we have u, v, and w, and we're trying to write x in terms of u, v, and w. So just by replacing vectors into this equation, I have -1, -2, -2, and it might be easier. Your textbook always writes these horizontally or as an ordered triple, but it might be easier to think of these as column vectors because of how familiar we are with matrix operations, which will come into play in this section. So this is the exact same thing. So hopefully you can see where I'm going with this. But what we're saying is we want to be able to write x as a linear combination. So we're trying to solve for a, b, and c, or you might see it as c1, c2, c3, and so forth. So how are we going to solve this? Again, we can think of it just like this, just like your textbook shows, and you can do some distributive property. So 0a, 1a, 4a, and so forth. And you can think about component-wise, -1 is equal to 0a plus -1b plus 3c, and then -2 is equal to 1a plus 1b plus 1c, and so forth. And you can write those three equations, and then that's just an algebraic equation. You can use substitution or elimination. Or you can think about this as the way that we just wrote it with column vectors. Now, two ways that you can finish that out. You can either write it as ax equals b. So I'm trying to tie this to things we already know how to do. Ax equals b and solve using the inverse. That a inverse b is going to be equal to x. Or you can write it as an augmented matrix. Notice b is that last column. And then you can solve using Gaussian or Gauss-Jordan elimination. So I'd like you to choose one of those methods and solve, and then we'll go through the solution together. Hopefully you did the math by hand. I'm going to cheat a little bit and use Desmos just for the sake of the length of the video. So one option is to take A, which is the coefficient matrix, and find the inverse. and multiply it by b. And in doing so, I get 1, -2, -1. The other option is to take the augmented matrix and simply row reduce it with Gaussian or Gauss-Jordan elimination. And again, that last column, 1, -2, -1, is our solution. As with any math problem, you should always then go back to the original question to be sure that you have, in fact, answered the question or understand what you found. So what we found was that the solution was 1, -2, -1, but the question said write x as a linear combination of vectors. So this is not a solution. These are the scalars that we're going to use. So we can say that -1, -2, -2 can be written as 1u minus 2v minus 1w. So minus 2v minus 1w. All of these representations mean the exact same thing. So you're going to get a little annoyed with me because I like to try to help you make those connections, that all of these three things are exactly the same. Up next, section 4.2, vector spaces.